Hello everyone, I am Smriti Sinha here and today we are going to study the topic electron displacement effect. So we are going to see some theory part related to this topic and then we'll move towards solving some MCQs. Let's begin with the theory part. So what is actually electronic displacement effect? So electronic displacement occurs when actually electrons move towards one side or one part of the molecule. So if you consider a molecule which has many R groups attached to each other and then some different atom attached to it, or you can consider it instead of R as many carbons also attached and one different atom. So the electron will move from one part of the molecule towards the other. It may be in such a way or in a aromatic ring, and this movement of electron from one part to the other part of molecule is called as electronic displacement. Electronic stands for electron and displacement stands for movement, and therefore it is known as electronic displacement reaction. Electronic displacement is important to study because it is responsible for chemical reactivity of some molecules or inertness of the other. So basically questions mainly come from this part, that which one is more reactive than other, or why this molecule is less reactive. So all the reason is hidden behind the electron displacement effect. So there are basically four different types of electronic displacement effect that you need to consider or study. So the first one is inductive effect, second resonance, third hyperconjugation, and fourth electromeric effect. So let's see one by one. So the first one is inductive effect. So what is actually inductive effect? So moving towards this part first, I would like to discuss with you. If I have a molecule in which there are two same atoms attached, in that case, the electron between these two atoms will be equally shared by the two. And these two electrons will remain at the center of both the atoms as it is equally shared. But suppose if you have two different atoms attached to each other, here again electrons will be shared between the two. But the thing is, this electron will not remain at the center. Instead, it will move towards the chlorine. Why? Because one atom is more electronegative than other. And this type of movement of electron is called as actually inductive effect. So when an organic molecule has polar covalent bond like this is called as polar covalent bond. Why polar? Because one molecule is electronegative and gets a delta negative sign, while other is electropositive and gets a delta positive sign, and therefore it is called as polar covalent bond. And if in such molecules polarity is induced in adjacent carbon by single bonds, this is called as inductive effect. So you can see same type of molecule like HCl it is, just the thing is we have carbons here. So the Cl being electronegative is going to pull the electrons of this bond towards itself, and therefore this carbon will get some positive charge. Now this carbon will pull the electron of next carbon towards itself, and therefore the next carbon will again get some positive charge. But remember, this carbon will get more positive charge as it is directly beside the Cl, and the other one will get less. And this type of effect is called as inductive effect. Now, what are the things we need to remember about inductive effect? The first thing we need to remember about the inductive effect is that electron will always move from low electronegative atom towards the more electronegative atom. So you need to always move your electron from low electronegative atom towards more electronegative atom. First thing. Second, there is always movement of sigma electrons. Remember, here no pi electrons are involved. Always there will be movement of only and only sigma electrons. Third, it is an permanent effect. It is not temporary, because always the electronegative atom will keep on pulling the electron towards itself. So it is always an permanent effect. Next, it depends on the distance. So as the distance of carbon atom increases from the electronegative atom, the intensity of this effect will decrease. And next is the types of inductive effect. So to these types of inductive effect, I will go on later. But these 5 points you need to remember while solving the questions of inductive effect. So inductive effect, if you see here in this type of molecule where there are large number of carbon, so the carbon which is besides chlorine will have the greater inductive effect than the other which is away from chlorine, and this will be having the least which is far away from chlorine, and here no inductive effect will be seen, because as distance increases the intensity of this effect decreases. Now, the direction of inductive effect is depending on the bonded groups, whether that bonded group is electronegative or electron positive. That will decide whether the inductive effect will be towards this group or away from the group. For suppose if your carbon is attached to some electropositive group or electronegative group, like if it is attached to iodine, that is electronegative group, so the electron will be pulled away from carbon, and if it is attached to magnesium, that is electron positive group, the electron will be given towards the carbon. So there are two types of inductive effect according to this, whether the carbon is getting the electron or whether the carbon is donating the electron. On basis of that, so first one is electron withdrawing or accepting groups. Second is electron donating or releasing groups. So electron withdrawing groups are actually electron negative groups, electronegative groups which actually pull the electron towards itself. Electron donating groups are actually electropositive groups which releases the electron from themselves. So if you see this example, which was our first example, in this if you see, you have chlorine. Chlorine is highly electronegative, and hence it will pull the electrons of carbon 1 and carbon 2 towards itself. And this chlorine will now start exhibiting electron withdrawing inductive effect, because it is withdrawing the electron towards itself. And this effect is also called as negative inductive effect. Withdrawal means negative, and therefore it is called as negative inductive effect, that is minus I effect. Some other groups other than chlorine which show this effect are nitro, cyano, carboxy, ester, and alkoxy. So all these groups, what they do, they pull the electron towards themselves, causing minus I effect or negative inductive effect. On the other hand, the alkyl groups, it may be any alkyl group, methyl, ethyl, propyl or isobutyl, any alkyl group will show electron releasing inductive effect, that is plus I effect to the carbon chain. Next is resonance. So what is resonance? So actually resonance is a condition where there is movement of pi electron. So we have seen in inductive effect there was movement of sigma electrons, but now in resonance there will be movement of pi electrons through pi bonds. So for resonance, the first condition is that your system should be conjugated. If you have conjugate system, means alternate, double and single bond in your system like this, then only resonance can occur. And therefore this type of effect, due to movement of these atoms or bonds, you can say, due to movement of this bond it occurs and causes polarity in the molecule, and is called as resonance effect or mesomeric effect. Now again, like inductive effect, here also resonance effect is of two types. First, positive resonance effect or plus R. It is also denoted by M because M stands for mesomeric. It is another word for resonance itself. So in exam, sometimes they give you the letter M, sometimes R. Both are one and the same. So positive resonance effect is denoted by plus R or plus M. Negative resonance effect is denoted by minus R or minus M. So let's see first positive resonance effect or electron donating or electron releasing effect, that is plus R effect. So if you have in your aromatic ring, this is a conjugated system, correct? Double, single, double, single, double, single. In this, if you have some electron donating group, if I take O negative here, now what happens in this group? This O negative will try to push the electron towards the benzene ring in this manner. So here you get various resonance structures like this. So again in the next, this will come here and this will go here. And in this way, this whole electron will keep on moving throughout the ring. So here, if the substituent group has lone pair of electrons or negative charge, which is attached to the pi bond or conjugated system of pi bond, that group will show this plus R effect. So it may be a negative charge or it may be electron, which is in conjugation with the aromatic ring, which can be pushed towards the aromatic ring, will show plus R effect. So the groups which show this plus R effect are OH, OR, O negative, NHR, halogen, etc., which have plus R effect. Remember, plus R effect increases electron density at ortho and para position. So I should make it clear. In this benzene ring, there is no ortho and para position. So many a times this is asked, where is the ortho and para position in this benzene ring? So there is no ortho and para position. But as soon as you place some group over here, it can be any group. So now ortho and para position comes into existence. So the carbon next to this carbon where group is attached is called as ortho. Next to ortho is meta and next to meta is para. But remember, in plus R effect, your electron density, that is negative charge, will be only and only seen at ortho and para position. There will be no electron density increase or negative sign seen on meta position. Next, negative resonance effect or electron withdrawing resonance effect, which is denoted by minus R effect. So if your substituent group has the tendency to withdraw electron from the benzene ring or the conjugated system, that means it is showing minus R effect. The groups which show minus R effect are CO2H, that is carboxylic acid, aldehydes, ketone, cyanide, nitro, ester. So you can see all carbonyl groups show this minus R effect. So let's see one example for this. If you have a benzene ring attached to your aldehyde, and now if you want to do this effect, so now this aldehyde, instead of donating electron, will try to pull the electron towards itself, causing a positive sign over here, because benzene ring has donated its electron, so it will get now positive sign instead of negative. And this positive sign will keep on revolving in the ring only and only at ortho and para position. That means this minus R effect is only and only seen again at ortho and para position, and minus R effect decreases the electron density at only ortho and para position. So whether it is plus R effect or minus R effect, only para and ortho positions are affected. Next is electrometric effect. What is electrometric effect? Actually, this is a temporary electronic effect which is seen in multiple bonded groups. Okay, so if you have a multiple bonded groups and if some reagent come close to it, there will be shifting of this bond, resulting in the formation of positive and negative charges due to this reagent. Once you remove this reagent, you will get your original compound back. That means it is a temporary effect. You need to remember this is a temporary effect. Resonance and inductive were the permanent effect, but this is a temporary effect and it is only and only seen in multiple bonded groups and in the presence of reagent. Once the reagent is removed, the things will become normal. Next is hyperconjugation effect. So hyperconjugation again is a permanent electronic effect and which actually explains the stability of carbocation, free radical or alkene. It is seen in delocalization of sigma electrons only. So remember, inductive effect and hyperconjugation are related to sigma bonds or sigma electron. Resonance and electromeric effect is related to pi electron or the multiple bonds. Now, if you have carbocation or any other free radical or alkene, so the carbon next to it, if it has hydrogen, the more number of hydrogen, the carbon next to this charge is called as alpha carbon. So the more number of hydrogen the alpha carbon will have, the more will be the conjugation effect. That is hyperconjugation effect. So double bonded also, if it have alpha carbon, and the more number of hydrogen on this alpha carbon, the more will be this hyperconjugate effect. Similarly, for this radical also, the carbon next to the radical carbon is alpha, and the more number of carbon hydrogen on this alpha carbon will show more hyperconjugation effect. So hyperconjugation effect is only related to sigma electrons of the CH bond next to the carbocation, alkene or free radical, which is called as alpha carbon. Now hyperconjugation effect stabilizes the carbocation. You can see that tertiary carbocation is more stable than secondary, secondary is more stable than primary, and primary more stable than methyl. Why? Because in tertiary carbocation, you have 3 alpha carbons. In secondary, you have 2 alpha carbons, and in primary 1, and in methyl there is no alpha carbon. So if you see in tertiary carbocation, there are 9 alpha hydrogens. In this secondary, there are 6. In primary, there are 3. And due to this increasing number of alpha hydrogens, hyperconjugation effect increases and therefore their stability increases. So now let's move towards the question answer session. That is this first question for today. The stability of 2,3-dimethyl but2-ene is more than 2-butene. So this can be explained in the terms of. So how could you explain this? So remember, first you need to draw the structure. So 2-butene. This is your 2-butene. Now, because to the second carbon double bond is there. Now at 2 and 3 position, add methyls. Balance the others. This is the structure for 2,3-dimethyl but2-ene. Now draw only the structure of 2-butene. Now you need to explain why this A structure is more stable than the B. So reason is correct that A structure is more stable than B because A structure have more number of alpha carbon. As it have more number of alpha carbon, it have more alpha protons, and hence here you can see total number of alpha proton to be 12. Here you can see only 6, and therefore A is more stable than B due to hyperconjugation, that is more number of alpha protons. Next, most likely representation of resonance structure of para-nitrophenoxide is. So para-nitrophenoxide can be represented most likely in most suitable way. Which one will be the correct structure for this? So if you draw the para-nitrophenoxide ion, so it is looking like this. This is the original. It is phenoxide ion, and to this on para it should be nitro. So it is para-nitrophenoxide ion. Now, if you start drawing its resonance structure, so if I start drawing its resonance structure, so you can see here, this negative charge will come here, this will shift here, this will come here. Now this you do not need to write like this, actually you will make it clear so that you don't get confused. So it is O negative, double bond O, and shift this negative here. So what you get is C, double bond O, bond here, then double bond N, O negative, O negative. Why? Because this O negative is showing plus R effect, so it will push its electron towards the benzene ring, while NO2 will show minus R effect, therefore it will pull the electrons from the benzene ring, and due to this you will get this possible structure. Okay, another thing to remember here is this is the normal para-nitrophenol. Obviously this phenoxide, this cannot be the most likely representation, because in this way the O negative is also not stable and nitro is also not stable, because O negative have tendency to push the electron and this has the tendency to pull. Okay, next this structure, obviously the nitro cannot have two double bond O. Next is this structure. This is one of the resonating structure which is possible, but this is not more stable because negative charge is more stable on the electronegative atom rather than on carbon, and therefore your more stable structure is option B that we have drawn here. Next, the plus I inductive effect is shown by. So which of the following functional group will show plus I inductive effect? So you know that all alkyl groups show plus I inductive effect, that is electron donating effect, and therefore that is CH3. Next, the minus I inductive effect is shown by. So which of the following groups will show minus I inductive effect? So minus I inductive effect is shown by electron withdrawing groups, means which withdraw the electron towards itself. So you know that alkyl cannot show this effect, so you will rule out all the alkyls. Left behind is the carboxylic acid, and therefore this one is showing the minus I effect, that is minus inductive effect. Next, the increasing order of plus I effect for H, CH3, C2H5 and C3H7 is. So in which order does this inductive effect increase? So remember, the more number of carbon, more will be the plus I effect. Okay, because more will be the electron releasing capacity. So more number of carbon is in propyl, then in ethyl, then in methyl, and then in hydrogen. So the more who will show, propyl will show more plus I effect because more number of electron releasing carbons, then ethyl, then methyl, then hydrogen, and therefore option first. Next, shifting of electrons of a multiple bonds under the influence of reagent is. So if you are shifting a multiple bond electron under the influence of a reagent, that is called as, just now we have seen this is actually called as, okay, sorry, this is actually called as electrometric effect, and this is a temporary effect. Next, the least stable resonance structure among the following is. So which of the following structure is least stable? So I will give you one hint. If the two atoms which are vicinal or which are neighbor of each other and they have same charge on it, they will be very, very unstable because both are electron deficient, and both electron deficient species beside each other, obviously unstable. If one is electron rich and one is electron deficient, it is stable. Both electron rich, again unstable. So you need to choose in such a way that where two electrons, here you need least stable, correct? For least stable, two same charges beside each other. Okay, so if you see such structure, you will find that is option A, which have two same charges beside each other, and therefore they are least stable one, because the two electron deficient carbon and nitrogen are unstabilizing each other. Next, hyperconjugation involves overlap of following orbitals. So what does hyperconjugation involve? So hyperconjugation actually involves overlap of sigma and pi orbital. So remember, hyperconjugation is seen in only sigma orbitals, but there is overlap of sigma and pi orbital. This is the question which is asked most of the time. So remember this. Next, in which of the following molecules inductive, mesomeric, and hyperconjugation effect operates? So which of the following molecule is such which shows all these three effects in it? Only one molecule is there which will show all these three effects in it. Okay, so if you see first, in the first structure, you can see only inductive effect. You cannot see resonance because there is no conjugation. You cannot yes, here hyperconjugation you can talk about, but not much. Okay, now for the sorry, for the second structure, if you see, you cannot talk about again mesomeric effect here because there is no conjugation. Inductive effect, yes, you can talk about somewhat, and hyperconjugation also you can talk by stability of alkene attached to alpha carbons. But for the structure third, if you see properly, you can even talk about inductive effect as you have this electron withdrawing group present. So it will pull the electron towards itself. You can even talk about mesomeric effect. So if I draw this structure properly, it looks somewhat like this. Okay, so you can talk about mesomeric effect also here. Okay, that is resonance because there is conjugation present, double, single, double. And you can even talk about the hyperconjugation because to this double bonded carbon, there is alpha carbons, and alpha carbon here 3 and here 2, that is total 5 alpha carbon. So hyperconjugation is also possible. So you can even talk about inductive, you can even talk about mesomeric, and you can even talk about hyperconjugation in the third structure, and therefore it is the correct answer. Next, in pyrrole, electron density is maximum on. So in pyrrole structure, where is the electron density maximum? For this. Now see, this is not at all like benzene ring. So here resonance is somewhat little different. You need to draw the resonating structure and find out the maximum electron density position. So first this electron moves here, okay, and then this bond will move here. And you get a negative charge at position 3. In the next one, you can move this negative charge here and this negative charge, actually this double bond over here, okay, or negative charge over here. Okay, now in the next one, you can shift this negative charge here and this negative charge here. Now what is happening actually? If you see, if you move the negative charge here, this negative charge is away from the positive charge, and hence now here the stability is more. Okay, but if you see in this structure, here the stability is less. Okay, because these two opposite charges are beside each other. Now talking about this, if you can move this resonating structure properly, you can even resonate it in opposite side. So you will get more stable structure, one more like this. Right? So there are two possible this structures, that is the negative charge at 3 and negative charge at 4. This one will be least stable. So which one is more stable? 3 and 4. And therefore your correct answer over here is option 2. Next, which one of the following is correct with respect to minus I effect of substituent? Means which one of the following will show more minus I effect than the other? So you have here three types of groups. One is fluorine, the other is OR, that is ether, and next is NH2, that is amine. So remember, you have to concentrate on fluorine, oxygen, and nitrogen. So according to our periodicity trend, fluorine is more electronegative than oxygen. Oxygen is more electronegative than nitrogen. Means fluorine will pull more electron than oxygen. Oxygen will pull more electron than nitrogen. And therefore, the minus I effect will be in the same sequence, because more the electron pull, more is the minus I effect. And therefore, your correct answer is option B. That is, fluorine is showing more minus I effect than OR, and OR is showing more minus I effect than NH2. Next, which of the following carbocation is expected to be most stable? So there are 4 carbocations with you, and you need to tell that which one is the most stable one. Okay, so if you see here, now carbocation in the first structure is present over here, that is meta to nitrogen, nitro. Next, in the second structure, it is present near the nitro itself. In the third structure, it is present para to nitro. And in the fourth structure, again, it is present on the nitro itself. Now remember, nitro is an electron pooling group. That is, it is showing minus I effect. And if it is showing minus I effect and positive charge is beside that same group, that will be very unstable, because already nitro is pulling the electron, making this carbon already electron deficient. And again, on top of that, if you are putting a positive charge over here, this will become more and more unstable. Therefore, positive charge near the nitro carbon itself is very unstable. Therefore, here 2 and 4 options are ruled out. Now left with 1 and 3. If you see in the 1, that this positive charge is in resonance, means it is in conjugation with the pi bond. In 3 also, this positive charge is in conjugation with the pi bond. But in the 1, the nitro group is meta to this positive charge, and in 3, nitro is para. So we have seen that the minus R effect only affects the ortho and para position. Means if it is at ortho and para, positive charge is present, and nitro is again going to affect this ortho and para, means this carbon is already electron deficient. Now it is going to become more electron deficient due to nitro, and it will become more unstable. So this option is sorry. So this option is also ruled out. Now you are left with only the first option, as the positive charge is present on meta. So this nitro group is not going to affect this meta at all, and this positive charge will be well stabilized. Sorry, and this positive charge will be well stabilized over here rather than on para or on the carbon where already nitro is present. Next, match the pair column A and column B. So column A have their effects and column B have some definition, you can say, or description of this effect. You need to match it. So the first, inductive effect. Inductive effect is only the movement of sigma electrons, that is displacement of sigma electron. So one matches with your D, that is displacement of sigma electron. Second is hyperconjugation. Hyperconjugation is actually delocalization of sigma electron. Okay, because there will be movement of sigma electron like in resonance. So here it is C. Third is resonance. Resonance is the delocalization of pi electron, not displacement but delocalization. So it is A. Next, which of the following is an application of mesomeric effect? So mesomeric effect means resonance effect. So which of the following will be the application of resonance effect? So you need to tell that. So first, dipole moment. Yes, dipole moment can be known by the resonance effect. Next, strength of acids and bases. Yes, you can know the strength of acid and base by resonance effect. Bond length. Yes, this is also true. That is mentioned all of the above. So resonance effect can tell you that which group is electronegative and electropositive, that causes the polarity in the molecule, that is dipole moment. Next, strength of acid and bases can also be explained by resonance effect, and therefore here you can say that this type of acid, or you can take another example, a simpler one rather than this, that phenol and alcohols you can compare and tell that both has O negative, that is one is phenoxide ion and one is alkoxide ion. This is phenol and alcohol, but phenol can donate its proton very easily and it is acid, but alcohol cannot donate its proton and it is not an acid at all, it is neutral. So you can explain this on the basis of actually resonance effect, because due to resonance effect this phenoxide ion is stabilized and which causes this as a strong acid than the alcohol. Okay, so strength of acid and bases can be explained. Next, bond length. Yes, bond length can be also explained. Now, alcohol RO bond is longer than the phenol, oxygen and carbon bond. Why? Because both have carbon and oxygen bond itself, but this bond is longer and this is shorter, because this bond can form a double bond, and as it can form double bond, you know that length of double bond is short than the single bond, and therefore bond length can also be explained, and therefore the answer is all of the mentioned. Next, greater the number of resonating structure for a given intermediate. So remember, more the number of resonating structure means that there will be more stability. So the benzene ring is less stable than phenol, because in benzene there are only two resonating structures possible. Okay, but in phenol there are various resonance structure possible. So actually in phenol 5 resonating structures are possible, in benzene only 2. Therefore phenol is more stable than benzene, and hence the more number the resonating structure, more will be the stability. Next, how many tautomers can you draw for the following ketone? So you are provided with a ketone and you need to draw a tautomer. Remember, now for tautomer, you need to know that you should have alpha protons. If you have alpha protons, then only you can draw these tautomers. So I have 2 alpha carbons, means at both carbon I have at least 1 alpha proton. So 2 tautomers are actually possible. For tautomers, you need to just move your hydrogen from here, draw a double bond and make it OH. So this is the first tautomer. And this is the second. So 2 tautomers possible for this ketone. Therefore, option B is correct. Next, which of the following is a tautomer of phenol? Now, this is the structure of phenol. If you try to draw the tautomer for this, you need to now move this double bond over here and the hydrogen other way side. So it becomes like this. So this is actually the tautomer for phenol. And if you see here, the structure C is correct. Next, in keto-enol form, from presence of which type of hydrogen is must? So if you want to form a keto-enol form, which type of hydrogen you need? This is the keto-enol form for acetone. So which type of hydrogen do I need? I need alpha hydrogen, means hydrogen present on this alpha carbon. So answer is option A. Next, which of the following structure can show tautomerism? So out of this structure, you need to select the correct structure which shows tautomerism. So for tautomerism, as we have seen that we need alpha carbon having hydrogen. So if you see here, this is the carbonyl carbon, next carbon is alpha. They don't have here hydrogens. It means they have, but they have alkene also, double bond also. So this hydrogen cannot move. So this structure cannot show. And this alpha carbon should be sp3 hybridized. Remember, here also alpha carbon is there and here hydrogen is sp3 hybridized. So they can show the tautomerism. So second is correct. But for third, again, there are alpha hydrogens at double bonded, so it cannot show. So only 2 can show the tautomerism. Next, assertion. Electromeric effect is brought into play only at the requirement of the reagent. Okay, so what they are saying that electromeric effect is only seen when reagent is present, which is correct statement. Reason? It is a temporary effect. Yes, it is temporary, in which bond pair is shifted to one of the constituent atoms. Correct? It is a temporary effect and the bond pair of electron shifts to one of the atom due to this reagent, and therefore you can say that this reason is also correct, and reason is actually a correct explanation for your assertion, and therefore this is option A. Next, assertion: when inductive and electromeric effects operate in opposite direction, the inductive effect predominates. So what they saying that when inductive and electromeric effect both are operating in opposite direction, the inductive effect predominates. That is wrong. Actually, electromeric effect predominates because it is in the presence of reagent, and that reagent is present. That means that effect will be more strong. Reason: inductive effect is the complete transfer of shared pi electrons. So this word itself makes this statement wrong because it is not the complete transfer of pi electrons. It is the just the displacement of sigma electron, not the delocalization or transfer, but the displacement of sigma electron. So in this case, the assertion and reason both are incorrect. That is option D. Next, match the ions given in column 1 with their nature in column 2. So you have to see these ions and match them according to their nature in column 2. So it is not necessary that you will get only one answer. You can make as many correlations as you can. Okay, so for the first, if you see here, you can see here inductive effect also correct. Here there is a carbocation also. So many things are there. So first you can see that here the stability can be due to resonance too, because this lone pair of electron is in resonance with the carbon. So here first can match with A, that is stabilization due to resonance. It can even match with the B because there is stabilization due to inductive effect also, and it can even match with D because this carbocation is a secondary nature. So these three are the answer for the first. Next, fluorine. 3 fluorines are attached to the carbocation. So you know that now carbocation here in this case is attached to 3 electronegative atom. This electronegative atom will pull the electron towards themselves, making this carbocation more unstable because already this carbocation is having electron deficiency. Now this fluorine is causing more electron deficiency. So this carbocation is becoming more stable due to minus I effect, and therefore here is B. For the third one, also if you see, this is a negative charge and 3 alkyl groups attached here. Now alkyl groups are going to donate electron, that is by plus I effect, but now the minus charge is there on carbon, means carbon is already electron rich and alkyl groups are donating more electron towards it, means they are making it more unstable, and therefore here destabilization is there again due to minus I effect, that is inductive effect, that is B. For next, this is a carbocation which is attached to 2 more groups, so it is a secondary carbocation, so obviously D is correct. And here stabilization is also there due to hyperconjugation because 2 alpha carbon with 6 alpha protons, and therefore C is also correct. Next, which of this molecule is not a resonance form of? So you have this structure and you need to tell which of this following will not show the correct resonance form of this structure. Okay, so if you see, you can move this negative charge here and make a new negative charge here. So you get this structure if you draw it properly. Okay, so A structure is correct because I am able to get that structure. Now for B, if you see here, now if you push this negative charge here, and this double bond will form next negative charge here. So now the structure you get is so this is structure B if you see. So B is also correct. Next, now you can push this charge here and get a negative charge here, which is not there in any of the structure. So leave it. Now next, what you can do more is you can push this negative charge other way around. So now instead of rotating this charge in the benzene ring, it have one more possibility that you can shift this negative charge here and make it O negative, because this is also resonance possible, right? Like tautomerism. So C is also correct structure. Now you will say then about D. Yes, D is wrong structure because this negative charge can move in this direction, but can't jump here directly. It cannot be like this. It cannot, because there is no conjugation. It will come back in this direction but can't go this side. So D is the wrong structure, and therefore your correct answer is option D. Next, which of these molecules represents a pair of resonance form? So you have the following molecule, and which one will show the correct resonance form pair? So for the first, if you see here, this is trans, because two same groups on opposite end. This is cis, two same group on the same end. So this is not resonance. Actually, this is geometrical isomer. This is not possible at all because this is actually photochemistry. So not here, because you cannot break the sigma bonds. Okay, the counting of pi and sigma bond will always remain same. Next for this is actually tautomerism. You cannot say this is resonance because there is shifting of proton, correct? Now for C, if you say yes, it can be a resonance, because if you shift this bond over here and this over here, you get a positive charge created, and due to this movement of electron, positive charge can be created here. So C is the correct resonance form. Next, arrange the following groups in order of decreasing minus I effect. So you have to arrange according to decreasing, means first you have to keep the group which is showing more minus I effect, means more electron withdrawing effect. So you need to find out which of the following is showing more electron negative effect. So remember that in all these cases, if you see the nitrile, remember the sequence. Nitrile is more electronegative for pulling the electron than the acid. Then comes our halogens, fluorine, chlorine, bromine, iodine, as in periodic table they are given, because fluorine is the most electronegative and iodine is the least, and then hydrogen. In the same order, the minus I effect will also keep on decreasing. So nitrile being more electron pooling effect will show more minus I effect, then acid, then fluorine, then chlorine, then bromine, then iodine, and then hydrogen. And therefore option D is correct. Next, arrange the following groups in the order of decreasing plus I effect. So according to decreasing plus I effect, you need to arrange it. So more the group can donate electron, more will be the plus I effect. So remember, now you are talking about a negative charge, not a positive. So this negative charge shows a plus I effect by donating electron. Okay, so obviously this benzene with O negative will have more effect, okay, than the carbonyl with O negative. Then obviously the alkyl group, more the number of alkyl group, more will be the plus I effect. Here the less number of alkyl group, less plus I effect, and finally the hydrogen. That is option A is correct. Next, find out the incorrect statement about resonance. So which statement is incorrect about resonance? First statement, resonance structure should have equal energy. This is correct statement. Remember, if you are drawing two resonance structure, I will take a simple example of benzene. Both the resonance structure always have the same energy, and therefore they are shown by this arrow, means just the movement of electron, nothing else. Next, in resonance structure, constituent atoms must be in the same position, correct? Your atoms never move from their position. Whatever will be their position, that will remain the same, only there will be movement of electron. Next, in resonance structure, there should not be same number of electron pair. This is false because there should be always same number of electron pair. So the incorrect statement is C. Always the electron pair, if it is 6 here, 6 pi electron, in the next structure should also be 6 pi electron. Even though if you're taking a negative charge into consideration, negative charge will also be counted as 2 electrons, correct? So that will also be having the same number of electrons. Next, resonance structure should differ only location of electrons around the atoms, correct? See, if you see the resonance structure, they only differ in the location of the electron, means position of electron, not in the position of atom. So your incorrect statement is option C. Next, select the correct statement from the following option. So you have to select the correct statement out of this. First, conjugate effect is stronger than minus I effect. Conjugate effect is weaker than minus I effect and same as minus I effect. So best example for this to explain is your benzene ring having any halogen. It can be chlorine, bromine or iodine. Now, chlorine, bromine or iodine, any halogen is actually showing minus I effect. But if you attach it to the aromatic ring, sorry, it shows plus R effect. So what is happening? Why this minus I is going to plus R? Because this Cl have lone pair of electron, and because of this lone pair of electron, it can show the plus R effect by donating it. But this Cl even have the electronegative nature, so it is showing the minus I effect. But remember, when it is attached to the benzene ring, in that case, the plus R effect is much stronger than the minus I effect. And therefore, you can say that conjugate effect, that is resonance effect, is much stronger than the minus I effect. And therefore, any halogen attached to benzene will always show plus R effect, that is electron donating effect instead of electron pooling effect. And therefore, option A is correct. Next, select the incorrect statement. So first, electron withdrawing inductive effect of carbonyl group of COOH group weakens the OH bond and favors ionization. This is correct because if there is electron withdrawing group of carbonyl, that actually makes this COH bond weak, releases the proton and shows acidic nature, and make this as a strong acid than alcohol. Okay, but in alcohol, if you see, the same type of bond is present, but the problem is here there is no carbonyl carbon, no inductive effect, and because of which this bond cannot be broken easily. Next, inductive effect of chlorine destabilizes the acid and stabilizes the conjugate base. This is correct. The chlorine is showing minus I effect, as I have told. If you talk about acid, in acid, the positive side will be destabilized by the chlorine, but yes, the conjugate base can be stabilized by chlorine because conjugate base will have negative charge, and this negative charge can be only stabilized by electron pooling effect because it have more electrons, so that can be pulled further and stabilized. Next, aniline is a weaker base than ammonia. This is also correct. Aniline is a weaker base than ammonia because basis means the ability to donate electron. This is the property to donate electron. Ammonia can easily donate this electron, but in aniline, this electron is in resonance and therefore it cannot be donated easily, and therefore it is a weaker base. Next, phenol is weaker acid than water. Yes, phenol is actually stronger acid than water because once the phenol donates its proton, see, once phenol donates its proton, it forms phenoxide ion. This phenoxide ion is highly stable due to resonance, and as its conjugate base is highly stable, so it can donate the proton very easily to get this stability, and therefore phenol is actually stronger acid. But in case of water, once water donates proton, it gets hydroxide ion, which is not much stable. Next, which of the following is a temporary effect brought into play at the requirement of attacking reagent? So which is the temporary effect and is present only in the presence of reagent? That is electromeric effect, that is option C. And with this, we end today's session. Thank you. And thank you for watching our video. If you like it, please give me a thumbs up, that is a like, and then please share this video, subscribe this channel, and stay tuned. Thank you.